In this recording, I will show how to use some less known features of Excel to explore and analyze regression analysis in the case of a straight line regression. In the very first part, we will actually simulate data that we will analyze after that. We will do so by setting up an x variable, which will vary from -5 to 5. A y variable which depends on x according to a straight line regression formula, and then we'll add noise to it using a normal random number simulation, and then after that we combine the y values, the true y values, with the noise variables to get the noised response, and we'll analyze that with Excel functionalities. So let's make a room for putting the data. I'll put that in row 10. In row 10, I will define something that we'll call x var, then y true as the true values, error, and y observed, the observed value after simulation. So we do go from -5 in steps of 1 in this example to +5. Which gets us to row 21, and then we will need a formula, a linear formula, to get the true y values. So if we want to have this, what we would like to have is something that has an intercept as a parameter and which has a slope, and I will call it slop here to avoid confusion with names of inbuilt functions, although this is not necessary here. And we need a error variability, which I will call sigma. Let's start off with values of 0, 1, and 1. That means it's a straight line situation of y equals x. And we have a standard error of variability, which is of the size 1. The first thing that I would like to show in Excel is to define automatically names, which then make formulas more easy to read. I will select this range here and go in the formulas menu and say that I would like to create names from this selection, and it will propose automatically that it creates them from the left column. Make sure if you use names that you use names which are long enough. Excel cell references can have up to 3 letters, A, B, C, G, F, H, or something like that. If you use short names, they can get confused with cell references. So use 4 letters only. So let's see what this did, this command. If we select the cell B2, we will see in the box up there, which is called the name box, enter. And if we put ourselves in the B3, we have slop, and here we have sigma. So what we can do is to use these to define the regression formula. What we want to have is that the true y values are equal to the intercept plus slop times the x values. Remember, if you want to copy a formula downward, we go to the right edge of the cell until the selection cross becomes black. Double click, this fills in the formula. Now we have to generate error variability. Error variability can be constructed from the inverse normal probability function and a uniform random variable. So let me show you what the formula looks like. Norm inv, this is the inverse normal distribution function, and we will put in as an argument rand. This creates a uniform 0-1 random variable, and we will use a average, a mean of 0, and a standard deviation equal to sigma. Already you see here, if I now point to the cell B4, which contains sigma, to select that cell to be in the formula, it will propose automatically to put in the name, which makes reading the formula after that a lot easier. So let's close that here. And we see that this gets a number. You see, if we repeat this 11 times, we get 11 different numbers. They vary roughly from -2 to +2. This should be expected from a normal distribution. Interesting that the function rand, which produces the uniform random variate, is volatile. That means every time we recalculate anything in the Excel spreadsheet, it gets recalculated. So every time we do something on the spreadsheet, we will have a resimulation, a new simulation of errors. If we don't want that, we have to select this and freeze it. That means we copy and we paste it as values. So what we would do is you would copy and say we want to paste it as values. Now the formulas are gone. Let's go back to what we have because we want to stay in simulation mode. So here we are. So the observed y values are the true y values plus the errors, and so we can here copy down and we get this situation. What we can do now is to display all of this in terms of an XY graph. We will use for that the x values in x. The true y values we will display as a line so that we see what the truth is. And then we will display the observations as points. The errors we don't display here. So let's create a first graph here. Insert xy. What we want here is a graph just as a line with no points in there, and we get that. Now let's work that up a little bit so that it's nicer to look at. We will not need, well, let's leave the labels in there. It doesn't hurt. What we will certainly do is to take the grid lines away, or we will turn them very light gray so that they're not too prominent on the picture. So let's take them away. Something else that is sometimes useful if we make a graph like that is to get the axis label out of the way. Here we put them low. Same thing here, put them low. Now the x values are fixed, the y values can vary with the simulation. I would like to get a fixed axis just to make sure that we have enough room. I will go from -8 to 8. So now we have this straight line. This is the truth. And we will now add the data points as a new series. And we can either type it in or we can link it to a cell. We'll do that here. We need the same x values and we need as y values the observed ones. Now obviously it will by default use the same type as we had before. That means a line type. We still have to change that to a point type. So here we have the situation with the true and the observed data points, and we can just press on F9 to see how they change around the true line by simulation. Already gets you an idea on the stability with which we can estimate that line. Now an estimation in Excel can be done two ways. One way, if you just want to have the equation displayed on the graph, we can simply say add trend line. By default, this will make a linear fit. And we can also then decide that we want to display the equation on the graph. Something else that is sometimes useful in making graphs is to take away the outer frame. This makes it easier to look at, nicer. So let's do again simulation. We see that the black line now moves around, moves about the blue line. This gives you an idea with which precision we will be able to estimate the blue line from data which are actually simulated from it with an error of a standard deviation of 1. Good. This was the first part of it. Now we will try to retrieve the equation and to build the predicted curve, not using the trend line, but using direct Excel formulas. So for this purpose, I will take it away. So now it's not shown anymore, and I will show you two other functions that you can use in that context. One is called intercept. There we have to select the observed values and the x values and slope. And there's also a function that is called STEYX, which is the standard error of residual for a straight line regression. So again, we select the known y's and the x's to it, and there we get it, or we don't. Here we must have made a little mistake. We selected the x values from A12 to A21 instead from A11 to A21. There we go. So here again, pressing F9 resimulates, and we see, I hope you see this here, I will round it a little bit so that it's easier. That's maybe a bit too much rounding. If we resimulate this a couple of times, we will see that the estimates are around the actual values that we specified here. Let's make this sure that this actually follows. Let's make a slope of 2 instead of it. And let's see what happens here. F9, F9, F9. Yes, now this cell here follows around 2. Let's turn this off, take it 1 again, and let's make more standard error. Let's see what happens here. Yes, indeed, now this cell is close to 2. There we go. Let's go back to the original situation. Now, if we have this kind of setup, that we have the coefficients here and the standard deviation there, we can now also get the predicted value y fit, or the fitted values, which is better to say, and we can calculate that either by a direct formula or using something, and I will introduce that here, a matrix formula. So what we really want to do is for every combination, every value of x, what we would like to have is the estimated intercept, and I will freeze the number here, plus the estimated slope times x var. This evaluates the equation. Let us stick it over there. Let's add another curve here, another set of points. This is y fit. The x values are sitting here. The y values are sitting there. And we want again, no, this was wrong here. I have to get the x values here. And then we have to get the y values. And we select OK. Now, since we had the previous as a set of points, this will again be displayed. No, it's here as a line, so that's, we don't have to change that anymore. That's very good. So let's see here, and this is what we had before, that the estimated line, which is now green, moves about the true line according to the points that we simulated. Now, I said we will use a matrix function here. So here it is calculated as a direct formula, but this can also be seen as a matrix formula, and we will show that in the next video, in which we will go from a straight line regression to a multiple regression. Thanks for listening.